while we wait for
Recording
the.
in progress.
There it is. So I think you can all hear me. If I speak without a microphone, I'll try to speak loud. So good evening. Good evening. My pleasure to welcome you tonight in person to Heinz R. Pagel's lecture, one of the weekly series of summer lectures brought to you by the Aspen. Greg, critical biophysicist at the University of Amsterdam and graduate university in Japan. Tonight, I'll be your host and moderator. Before I introduce our speaker, Vincenzo, let me introduce you both to the center and to the public lecture series. Aspen Center for Physics, now over 60 years old, brings to its campus about 1,000 scientists each year, roughly equal numbers to participate in summer workshops like today and winter conferences. Week-long winter conferences address cutting-edge research topics across all branches of physics. In the summer, physicists come more extended physics that enable them to participate and collaborate with colleagues from around the world. The unique informal setting of the center lends itself to the incubation of new ideas and a number of important advances in physics were first made at the center. The center is a nonprofit institution, and our participants are partially supported by grants from the National Science Foundation and the Simons Foundation. We are gratefully welcome any and all donation. Public lecture series of all you here tonight is named in honor and in memory of Heinz Pagel's, who is a professor of physics at Rockefeller University, president of New York Academy of Sciences, a trustee of the Aspen Institute, and a member of the Aspen Center for Physics for 20 years, serving as a participant, officer, and trustee. Heinz was known for his contributions to the physics of elementary particles and cosmology, among others, and for his effective dissemination of scientific knowledge to the public through books and lectures. Local resident of Aspen, he died tragically in a car accident on Pier Peak in 1988. We request that all participants in tonight's event conduct themselves in a manner that is welcoming to all participants, treat each other with respect and consideration, free from any form of discrimination, harassment, or retaliation, creating a supportive environment to enable scientific discourse, essential to the mission of the center. There are programs on the table outside the hall, so you already have them. Please come back for our next public lecture next week on quantum matter out of equilibrium. That will be given by our committee of Stanford University. Now let me introduce tonight's speaker, Vincenzo Vitelli. Vincenzo is professor in the Department of Physics, as well as the James Frank Institute and the Karnoff Center for Theoretical Physics at the University of Chicago. Received his PhD at Harvard, was a postdoc at the University of Pennsylvania, and was previously a professor in Leiden University in the Netherlands. He is expert in condensed matter theory, where he's made important contributions to a broad array of topics, including recently matter, machine learning, metamaterials, topological insulators, hydrodynamics, dynamical systems, liquid crystals, granular media, glasses, and polymers. From that list, you can see that his creative mind isn't confined by traditional academic boundaries. We're very lucky that Vincenzo was an organizer of the workshop that we're in today, and also that he's with us here tonight. Vincenzo, welcome, and we look forward to it.
Hello, everybody. I hope you can hear me. It's a special privilege to be here and to take you through this journey into robots, living system, and machine learning. The first thing I'd like to say is that if you have any questions during the talk, feel free to just ask it. Interrupt, and that's great. If you want to ask it at the end, that's also good, but would welcome interaction. In fact, it's much nicer to have a dialogue, not just a monologue, and I can shorten this talk on the fly. Please, feel free. Okay. So I would like to talk about a rather unconventional list of topics for theoretical physics. Almost nothing in here is really physics. Robots probably evokes engineering, system biology, and machine learning evoke computer science. I'd like to start by saying a word about the physics, the standard picture of physics. This is the physics that I was taught when I first fell in love with the subject. And in retrospect, it seems a bit dull. It's balls connected by springs. It's the standard machinery of mechanics. And Now, this is perhaps simplifies one of the central tenets of physics. You can understand a lot in the world just thinking about one idea, minimizing energy. Okay, if you push, for example, on this media composed of masses and springs, after maybe rattling a little bit back and forward, will just settle into an equilibrium configuration where all the springs are there resting. Physicists understand an enormous array of situations by picturing physical systems as if they were a ball that moves in an energy landscape or in a potential energy, like this sombrero hat. So you could imagine that the physical system is like this ball that comes down, rolls up and down a bit, and in the end it rests in a position at the bottom of that, in the valley, if you like, of this landscape. This picture that pervades physics and many other subjects is tightly connected to the notion of equilibrium. Dynamics of a physical system often tends towards a state of equilibrium, where it stops. That ball will stop moving. The things I like to talk today do not fit that framework. And in particular, I would like to tell you about systems, some of which inspire biology, neuroscience, even physics, which have one feature. First of all, the way they move, the dynamics of that system, cannot be understood purely in terms of an energy landscape and motion in an energy landscape. This is one example of that, which I would like to introduce right now here. This is an idea that stretches also in other domains like economics, neuroscience, ecology. It's the following. If your system is composed to multiple species, or at least two species, it could be particles or it could be animals that interact with each other in a non-mutual way or a non-symmetric or non-reciprocal way, then typically we can't understand this system using the standard notion of equilibrium and rolling down in a potential. One example is this picture here. See here a rabbit, which is a predator, a rather sweet-looking one, and a carrot, which is the prey. Now, clearly, the population of carrots affects how many rabbits you're going to have around. But the way the rabbit interacts with the carrots is very different from the way the carrots interact with the rabbit. I mean, it is manifestly true. You probably don't need a theoretical physicist to figure that out. But this is exactly what we call non-mutual interactions. For example, sometime in the laws of mechanics that you're taught in physics school, you have Newton's third law. The way A interacts with B is equal and opposite to the way B interacts with A. That's the paradigm for reciprocal interactions. These are manifestly not. Another example is actually what goes on presumably in our brains. Our brains are a network, can be pictured in a simplified way. There's a network of neurons. Some of these neurons are inhibitory, some are excitatory, and as their name denotes, they have different actions on each other. So whenever you have this complexity of a system with non-mutual or non-symmetric interactions, typically you need to do something more complicated to understand their behavior. And I would like to give you a very concrete sense of what that could be, using some demonstrations with robots. Okay? Some people like to call this approach of using robotics to illustrate physics laws as robophysics. This is what happens when you put together many such robots, collective robotics. Let me start simple. One ideal model that physicists like to study a lot is represented minimalistically in this picture here. Imagine having a bunch of arrows. These arrows, when there is a lot of noise, are oriented in random directions, but they have a tendency to want to align. So if the tendency to align is stronger than the noise, then this arrow will all align in one direction, and the system will be ordered, unlike the picture shown here. What I would like to show you is a variant of this simple situation. Instead of having arrows all of one type, you're going to have two types of arrows. In fact, our arrows are going to be robots. You're going to have the red robots and the blue robots. And the crucial thing here is the following. These robots are programmed to have the following property. The red wants to align with the blue, but the blue wants to anti-align with the red. See, there is a frustration in the way this building block interact with each other. And almost intuitively, you could imagine how you're going to solve that frustration. Because one part of the system wants one thing, the other part wants a different thing. It's hard to imagine they're going to rest in a configuration where they're happy. Even at the level of a sort of linguistic metaphor, you imagine that they will run in circles, trying to find a configuration where they're both happy, being unsatisfied all the time. So instead of speculating, I want to show you what happens when I run the experiment in front of you. So again, the red wants to align with the red, the blue wants to align with the blue, but the red and blue wants to do opposite things to each other. What happens is the following. I don't know if you can see, in these systems, these tiny robots are constantly rotating. They're not rotating because each robot wants to rotate by itself. They're rotating because they can never be happy in any configuration. You can almost see it with my hands. Imagine that I'm the red robot and this is the blue robot. So the red robot wants to anti-align, so it takes the first step. The blue one wants to align, so it takes the next step. Then this dance continues ad infinitum. Literally, they're running in circles because they cannot solve the frustration inherent in the laws that we used to describe. This is a situation in which this system is not just sitting at the bottom of a potential in an equilibrium configuration. It's going around all the time. It doesn't stop. Now, one question that we can ask, and is the first thing I would like to ask, is that can we use these robotic building blocks to make the analog of those masses connected by springs that are a paradigm to understand the property of solids, and revisit mechanics, which is the first form of physics that people study in school, through the lenses of this active component, or this robotic component. Okay? I'm going to show you again another movie. This is from work done with my colleague Corentin Coulet at the University of Amsterdam and a bunch of great collaborators. Here you see another little device. It looks like, if you schematize, like two innocuous sticks connected by another one. But the thing that I would like to draw your attention to is that inside here, there are controllers and motors. This is by no means a passive structure. This is a structure that can move because there's a battery inside and they can sense the motion of these two sticks. I want to perform a very simple experiment that we can do with our finger and a very sophisticated experimental equipment. We're going to be touching, virtually, this end. When you touch this end, notice that this other end here is moving outwards. Now I'm going to repeat experiment the other side. I'm going to touch the right side instead of and watch what happens to the left one. Here you have a recording of what happened before. Now you're going to see finger coming the other side. Notice what's going on. When I push from the right, the left sticks come in. When I push from the left, the right thing goes out. There's an asymmetry in the way the second stick responds when I move the first, vice versa. Asymmetry is reminiscent of those two robots that wanted to align and anti-align. And mathematically, for those in the audience, remember springs and stuff like that, is represented by an equation like this. This is an object called a matrix. The crucial thing about this matrix is this component highlighted in red, where there is a minus. This minus means that when you touch one, two does one thing. When you touch two, one does its opposite, hence this minus sign. The presence of this minus sign is what makes these forces rather strange. They're forces that can harvest energy when you take around the loop of deformation. This is use the word non-conservative to denote this unusual behavior. This would be forbidden for a passive spring because it requires a source of energy, it requires a battery, but robots do have batteries. See? So what we want to think now is to build materials that are gigantic machines built out of little machines, as opposed to materials built out of atoms. And then we'll turn to even smaller machines that occur in the biological realm. Okay? Before doing that, let me show you the simplest thing. You could take that building block that you saw, we just make a ring out of it. Okay, you see, this is the same thing as before, you noticed, but we just closed it into a loop. And the first thing I want to do, which is rather boring, is the type of materials that perhaps you're used to, is to switch off the motors or the batteries that are inside here. And I'm going to touch it and show you what it does. We touch it, oscillates a little bit, and then goes back to the position which is happy. This is the normal elasticity, the normal mechanics that we learned in school. Now, I'm going to do a tiny change. I'm going to switch on the motors. I want to show you what happens to this robotic structure when I touch it. You'll see it's a very dramatic change. Gentle touch. It's going. Keep cycling. It doesn't stop. Please notice there's a wire. So there's somebody who's paying the bill in terms of energy, right? So what we would like to understand is we would like to characterize this cyclic motion. Okay? We want to take data from movies like this, from these robotic things, and try to analyze it, make sense of the cycle and why it occurs. Okay? It stopped only because the movie stopped. This thing will go on until the battery is off. Okay, in fact, the technical name for this cyclic motion is a limit cycle. And I want to illustrate what that means. So, first of all, these forces that happen in this structure can produce work on a cycle. It means that by moving around the cycle, this structure can generate energy. That's why it can keep moving, because any resistance from the friction in air or the substrate can be overcome by this energy that is continuously generated by virtue of the deformation. What you're going to see here, I'm going to replay this movie. Then on the right, I'm going to plot this cycle in terms of two coordinates. These coordinates are two modes of deformation of the structure. One is this square-like deformation, rectangle-like deformation. This other one is this rhombus-like deformation. The technical name for this deformation of a patch of material are two modes of shear deformation. That's how mechanical engineers would call them. Important part for the purpose of this talk is that when analyzed in these two coordinates, as these things move around, it traces a loop in this space. This is the limit cycle we were talking about. This limit cycle is possible because the strange forces in the robotic material create energy around the loop. When we first saw this, we said, okay, this sounds cool. It's also a bit unruly because you touch it and it starts doing all these crazy things. We actually use it for something. Okay, can we imagine this principle as a paradigm for some simple form of engineering? And the title of this talk is this slide is a bit cheeky, admittedly, the rediscovery of the wheel. But yes, I'm going to first ask you to rethink about what a wheel is. Look, I don't even have a car, but I do have an electric bike. My experiences with normal wheels are the following. There's a wheel. A wheel doesn't have to deform. It's connected to a shaft. The shaft is connected to a motor. The motor moves, the shaft transmits that motion, and then the wheel goes. Okay? The wheel doesn't have to deform in order to move. Now, this little robotic component works differently. Take a look at this movie. Notice this is an uphill direction. The wheel starts deforming a little bit. The more it deforms, the more it starts its cycle. The more it starts its cycle, the more it generates energy, and the more it can climb up. So this is not going to go on Pyramid Peak all the way, but it did climb probably what is this very limited slope. Okay. The interesting thing from our perspective, compared to a normal wheel, is that the amount it will deform depends also on the terrain on which you'll move. So let's repeat this movie on a rough terrain. I don't know if you can see here in white. This is our approximation of a mountainous terrain in which this adaptive wheel, odd wheel, is going to move. You'll see it again. Starts with this casual motion right there. Starts deforming even more as it hits all the bumps on this thing. And as it deforms, it generates more energy, and hence it can adjust the speed at which it climbs to the terrain. Now here, notice that it keeps persisting. It wants to really get out. It doesn't stop because it's programmed not to stop. Of course, this is a rigid surface, so it's going to be frustrated. So the idea that I would like to give you a sense is that this is just the simplest building block of a world of robots or machines. That's the most striking example is here. Here we've built a whole solid, if you like, out of this robotic component. It's a bit like the textbook example of pressing on a bunch of masses connected by springs. Now the masses connected by springs are these robots. Notice that when we throw down this weight, the robotic wall catches it and it throws it at an angle. Okay, it's a response that breaks left and right symmetry because those very peculiar interactions that I showed. It can also grab this object and throw it higher than it came down because these things have batteries in it. It's like a robotic armor. But
this actually relates to something that we talked about in our morning session. I'm wondering, can you view this as optimization of trying to throw it off at an angle? Like you change your optimization problem to something different. Can you view this as dynamics with optimization, just not usual energy based?
So there's not a physical quantity that we optimize. There's not an energy. But what we can do, if we wanted to have this angle, the angles at which we throw it to be maximal, for example, we could act on that matrix of forces and optimize the entries in a way that we can calculate with rational criteria. Now, I would like to give you a bit of a sense of what is the physics behind these machines built out of machines. This, when viewed like a solid, should be analyzable using the equation of elasticity. Elasticity is one of the oldest branches of physics. It describes how objects deform. It was invented to study masses connected by springs, not collection of robots, because they didn't exist in France or England when this theory was created. So we had to modify it in a way that could mathematically capture what's going on here and in the wheel example that I showed you. We literally need to understand, go behind the wheel and understand what's going on there. Actually, here I'm going to use some graphics from a very interesting article in a popular science magazine, Quantum magazine. When I read it, I thought, these guys understood our research probably better than us, so I'm going to use it. And there are two modes of deformation that I was talking about, this shear deformation. You could imagine taking a patch of the material, it is a square, you can turn it then either into a rhombus or into this rectangle-like shape. Now, usually these two modes of deformation do not mix with each other. If you try to do this, then the forces will correspond to this deformation. But in these strange materials that we have created, the robotic, the two will mix in a way that is going to be shown in this movie. Notice that when I'm going to replay it, it's going to replay, I think, automatically. See, when you try to do this, then it does also a little bit of that. When you try to do this deformation, it also mixes in a little bit of the other with an opposite sign. This is a very unusual form of elastic response that you will not find in books. And to do that, we had to change the time-honored equation of elasticity. We introduce new moduli. You see, engineers understand materials, the mechanical property of materials as follows. I press onto something, then there's a number called a moduli that tells me how the material is going to exercise a force back onto to me. And people have characterized all these moduli before, for literally a couple of hundred years. They always did it assuming that energy was conserved. This precludes the possibility of studying robotic materials that have energy sources. So in the case of this shear deformation, there's a moduli known for centuries called the shear modulus. The moment in which you have this robotic material, there is a new moduli, this K naught, which is responsible for all of these strange deformations, and ultimately also for the behavior of the wheel that can climb up using these strange contortions. The thing that I would like to draw your attention is that these equations shown here in this pictorial form represent the behavior of the material on very large scales, not at the level of the single building block. The fact that the single building block does not conserve energy because they have those peculiar interactions can be felt even at very large scales. The material does not forget at the very largest scale you broke conservation law at the micro scale, the conservation of energy that we love and learn. We don't really break conservation of energy. Don't think new crazy physicists say that conservation of energy doesn't exist. Well, it does exist. It's just that our system is a wire connected to something. The moment in which we look at that system, we are looking at an open system where we allow energy to flow in. We want to describe what is possible as a result of that. Now, this first part of this talk, has been very classical in the following sense. This is the thing. They have hypotheses, they have ideas, they write down equation, do experiments. The ideas, the hypotheses come first. When confronting more complicated systems than robotics, we may have to change that. You see, one thing that is cool in robotics is that we know exactly the building blocks for which these complicated things are made of, because we built it. But when we confront, it's like biology. Here I'm going to show you something that moves too. This is not a robot. This is a cell. It's a cell crawling. And what is imaged in this beautiful moving in colors is the density of something called molecular motors. These are motors that are extremely tiny, but philosophically equivalent to the one that the current Tom Cooley built in his own robots. But this has not been built by us. This has been built by nature. We want to understand how does this cell move? We know how that wheel moves because we built it. How does it move? And what is really complicated here is that the problem involves first proteins that are biochemical informations that encodes the mechanism of the mechanics of these molecular motors. And then there are many scales. The proteins are very tiny compared to the scale at which this cell is crawling. So what we would like to understand is figure out a way to go from the proteins, determine the biochemistry of this, to the physics of how these things move on a completely different scale. The colors are the density of a molecular motor called myosin, but this is a three-dimensional structure cell. So the color is the height at which this myosin density is being measured. Okay, so we decided to try a different approach here. Since we do not know, we do not have enough constraints of the physics to start with the hypothesis in which we believe in, draw conclusion and write equation, trying to use with a bunch of collaborators, Margaret Gardell and Patrick Oakes, who are our guides on the biology and biophysics side, and very talented PhD student, and Matt Schmidt and Jonathan Cole and Sala. We would like to use artificial intelligence to come to the rescue of this problem. We would like to input, and I'm going to explain to you what that means, into a machine learning model, all the biochemical information, trying to output the forces that this cell explores that enables it to crawl, very much like that robotic wheel was going uphill. But we want to learn the rules from data without making hypotheses. And we want artificial intelligence to discover those rules for us. A little bit of help from us. Okay? So before doing that, I want to explain to you in a way that is very approximate, very, if you like, schematic, how a neural network works. Remember, first I said the first part is classic. Hypothesis, we write down equation on a piece of paper, compare with data. Sounds simple, it can be very complicated, but it's a very established pipeline in physics for hundreds of years since Newton. We're going to change things a little bit. We're going to pose some questions. We want to build, if you like, a machine, neural network, something that emulates a little bit what goes on in our brains, that is going to answer the question that we're interested in for us. So let's start with a question that presumably doesn't need a lot of intelligence to figure out, at least for us. Is this a cat or a dog? Of course, this is not a cutting edge question of biology, I know. And similarly simple questions that people use as example is, do you recognize a digit that you hand draw, a 2 from a 3? The point is that we want to teach a computer to do that. How do you do that schematically? How do you build this so-called neural network? I'm going to try to show it to you in a couple of slides. Imagine that you take this black and white picture, grayscale picture of a cat. You're going to bring in some nodes, some these little dots, in which information from each pixel, this image, will be absorbed. We're going to call this nodes neurons. Okay? And then what we're going to do, we're going to have first a layer of neurons that takes information from each pixel, for example, its value of grayscale. Then we're going to have a second layer of neurons, which this information is processed according to some complicated mathematical manipulation that involve, besides a linear combination of the information coming from this layer, also what is called an activation function. It's a nonlinear function like this, goes from 0 to 1. It mimics a bit what happens in a real neuron, where the spike will only occur when the signal exceeds a certain threshold. Then we're going to have the information coming from each of these nodes. The left go to each of these neurons that are to the right, causing this very complicated maze of connections between these neurons. And we're going to do it again, until at the very end, we're going to output in the final layer just two numbers that are the probabilities of this object being a cat or a dog. If we do this by choosing these numbers randomly, well, the answer that you're going to get for this probability is not very informative. For example, this neural network predicted that this is 50% a cat, 50% a dog, which is not a very impressive performance. But the idea behind here is to repeat this with many images to train this neural network. What that means is that you have the idea of wanting to optimize probability of getting 1 for a cat. So what you do is you're going to update all of these links, where the W in the equation, to do that. And again, the scope of training this network in such a way that when it's shown that cat, it will give you the high number probability for being a cat and a low one for being a dog. You do this iteratively many times. And then when you show a new image of a cat or a dog that the neural network has never seen, then this network will be able to detect a cat from a dog. See, even if you don't follow all of these details, one thing I hope you can get. One, it looks bloody complicated, and it is. Second, it's a little bit like a black box. It's fundamentally different as an exercise and coming with a lot of intuition and writing down a simple equation on a piece of paper, which is how I was brought up as a physicist. It's really a different paradigm towards problem solving. Some people even question whether solving problem this way means understanding it or not, and probably it doesn't really. I want to show you that by using neural network and human intelligence, you can aid the process of scientific discovery. First of all, we're not really interested in distinguishing cats from dogs. There are more complicated questions in our mind. I want to return to the question of how a cell crawls on a substrate. How does it move? Okay. And I want to use neural network to answer that question. Okay. First of all, there is a physicist view of how a cell, or biophysicist view of how a cell interacts with the substrate. Physicists have a habit, at least me, to make oversimplifications. You would imagine that cells sticks to the substrate because there's something like a spring that connects the cell to the substrate. If we understand how he adheres, we have a hope also to understand how he moves. If you talk to a chemist, they're going to look at this and laugh because it's definitely an oversimplification. They're going to tell you, if you're lucky, it looks more or less like this. It's a huge number, and I mean, conservatively here, I listed all the one that my collaborator told me we should pay attention to. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 proteins. And of course, this, guys, you should imagine as a distribution in the cell. So it's a lot of information. And all of them are important for this process of adhesion. The question that we started asking is, could we get away by only knowing about a few of them, still be able to make inferences about the motion of this cell? All of them are important chemically. Maybe there's some redundancy in the information here. And if we know maybe 1 or 2 of them, maybe we know also about the others. How can we even test that? This is the question. Does an effective model require all of this knowledge of all of these proteins? Okay. This is a very typical situation in which, in the face of an enormous complexity of biological data, we need to reduce the number of variables that are important to just understand what's going on. Okay? And so the plan of action is to combine physics and chemistry using the following approach. Identify the proteins that are predictive of how a cell moves or how a cell generates forces. 2, build, using artificial intelligence, a chemophysical model that tells how the forces are generated and validate it with experiment, the old-fashioned scientific method way. So Let me show you what we do. Now, here, this slide, while complicated, is morally or immorally equivalent to the dog cat story. Except here, so we have this neural network. This is our black box. It is trying to make prediction. The one we want to predict is the distribution of forces, which are the arrows you see in this experiment that our colleagues can detect. The input, not a cat, is the density of these protons that our experimental colleague can also image. And of course, there is in principle 10 of them. This network is designed, it's shown many images of these fluorescent images of protons, many corresponding experimental picture of forces. Once you train it, if you show a new image of protons, it can output a picture of the force map that matches the experiment. Look at this too. See what has happened? We fed to this machine, this neural network, this image, and it outputted. This cell must have this force distribution. This is the reality that you have. It's a very striking similarity. We can even quantify it and put an error, make the error very, very tiny, to the point that we have no other methods of making predictions like this. Okay. Now, the most striking things to my eye was that we could achieve this type of accuracy using the density of only one protein. See what I'm saying? Initially, we thought that all of them were important, and they are important. If you knock them off biochemically, something changes. The point is that density of only one of them, called Zixen, seems to be correlated to the distribution of the other protein. By knowing only the density of one protein, we can make inferences about behavior. Motivated by that, we said, okay, can we push it even more, making prediction? But first of all, I want to show you that even other proteins like actin, myosin, paxillin can cause very good agreement between experiment and the machine learning prediction. And the interesting graph is this one here. See, this is a graph of error. The green one is this protein Zixen that we singled out. Interesting thing is that when you use Zixen and another protein like actin, the error is not much lower. That means that essentially there's not much to be gained by keeping all 10 of those proteins. With just one, we can achieve the accuracy. That was actually very striking and unexpected, not only to us, but also to our biology colleagues. Now, what I'm going to show you here is perhaps even more striking. Now, we wanted to understand whether the prediction of this neural network are robust. My experimental colleagues said, okay, we're going to go in and try to destroy this cell, perturb it. It's a violent chemical perturbation. We want to see whether the neural network can still predict the forces, even when we mess around with the biochemical composition. So what you're going to see here is we're going to mess around with myosin, which is one of the proteins that controls the molecular motors in the cell. And as a result of that, the shape of the cell will change dramatically. What you're going to see here on the left is a plot. Here there is the total force experienced by the cell versus time. There's going to be two lines. There are, in fact. The gray one is the experiment. The blue is the machine learning. Notice that they're on top of each other. They, in particular, also on top of each other after this time, roughly 25 seconds, when we apply this very dramatic change in the shape of the cell with what is called a washout. To make that more visual, I'm going to show you here on the left pictures of the cell, and on the right this graph, and they will move in tandem. You see that after this event, there are very, very strong changes in shape. Look at this. This is changing the force distribution quite dramatically, but still their machine learning prediction and the experimental one are right on top of each other. Our machine learning model is very robust. And what I want to stress is that this prediction are done on a cell that has never been seen before. It was not used to train that neural network. It's a new experiment that has been shown to that machine learning algorithm. Now, impressive as this may be, it's still a black box. We can predict, but we don't understand. This is very unsatisfactory, especially if you come from classical physics, where you put first the understanding in, and then you write down an equation based on that hypothesis of understanding. The question is, can we connect biochemistry to physics and extract a prediction and formulas from this machinery, from networks? So I would like to show you how normally physicists would approach this problem. They would write down an equation. This equation has 3 terms. It looks a bit intimidating, but one of them is how this cell contracts in the bulk. One of them, this one proportional to y, is how it adheres to the substrate, like sticking, like glue. The final one is a contractility just at the edge. And normally, it would fit some of this parameter, y, lambda, that are constant. You will make a prediction based on this formula for the force. Notice that the force predicted is uniform around the edge. Doesn't really look a lot like the experiment. It's not too bad, in particular, because this model was cooked up to reproduce reality. Notice that the machine learning is much better at predicting. If you compare this with this and this with that, here, clearly this is way better. So we were trying to think, okay, this has been created by human guesses. This has been created by artificial intelligence. And we try to understand, create something in between. Namely, try to figure out what is the machine learning doing by comparing it to formulas that we can understand. So how do we do that? Well, we said, what about sticking with these models, but trying to extract, using the machine learning from the data, important information on how these coefficients were put in by hand as numbers depend on the spatial distribution of protein, Zixen, we know is crucial from this phenomenon. So what we're going to do, actually, we're going to simplify this model. We're going to throw away the last piece. We now have only 2 terms. But we want this y not to be just a number, but we want to promote it to be a field. Field means something that changes as a function of position. For example, there could be more of this y in some parts of the cell and less in others. And you may ask, well, who tells you the dependence on space, this quantity y? Well, that we're going to learn it from data. In particular, since we know that Zixen is predictive, we're going to make y function of the density of Zixen. We know how this protein is distributed spatially. And we can construct a formula that is a hybrid between analytical work done by our brain plus information that we feed using machine learning. And we can construct a neural network that does precisely that. And I want to show you some of the results. So here is input, Zixen distribution. This is the experiment. These are machine learning prediction. And this is the parameter y, which is a function of space. That tells us that the protein is mostly concentrated at the edge. Using this, what we can do is we can build a model which is still mathematical, that as input from our machine learning, in the form of this, if you like, parameters that are a function of the density of protein that we learned is important for this phenomenon. So here we have nature, we're trying to match. This is our deep neural network that knows nothing about models. This is the model that knows nothing about machine learning. This is an hybrid that we created. This is a continuum theory. This is mathematics, but with input from our neural networks. Notice it does quite well in comparison to nature, compared to a model that was built purely with mathematics and no input from machine learning. Notice it doesn't do quite as well as our deep neural networks, because presumably our interpretation of what this deep neural network is doing is still too simple. It's a close approximate to reality, better than what we could do with our neural networks. So if you like, little note about modeling here is that we try to understand the nature. This is a plot of descriptiveness versus complexity. Okay, so deep neural networks are very high in descriptiveness. They match reality quite well, but they don't give many insights because it's a black box. We don't know what it's doing. Okay, one thing we do know, it's a useful tool to understand what input is relevant to create a certain output. The other extreme, we have models that are built using with mathematical physics. They're full of insights, but they don't always do a very good job at describing reality in detail. In between, there are these models that we create by combining mathematics and physics with machine learning. They have a high power of description, and at the same time, they're interpretable because we know what goes on, we know where we put the key ingredients. Now, strong of these successes, we decided to apply these techniques to other systems. This is a system which is truly fascinating, fruit fly embryogenesis. All these movies here from the laboratory of my friend and colleague, Sebastian Stragan, who is in the audience at the very end. He's going to shout if I butcher the beauty of biology. So the thing that Sebastian has devoted a good part of his career is to understand how this egg, if you like, the fruit fly, as time progresses, transforms into a fly. So it undergoes this very dramatic changes. On top of this fruit fly, you see cells that are moving. And as they move, also the shape of this egg starts changing. And it changes quite dramatically. I mean, eventually this thing is going to become a fly. And there is a number of minutes this is taking. And of course, this is a movie that is much sped up. Now, besides imaging all these cells moving on the surface of this complex embryo, what Sebastian can also do is he can also image the distribution of proteins on top, very much as was done in the previous example with the fourth generation. This is a protein called cadherin, and this picture shows the density of this protein in this on the surface of this embryo. What we would like to do here, and this is a work in collaboration with Jonathan Colin, Noah, Nicholas, and of course Sebastian. And the idea here is we're able to understand, using the same technique as before, there are only two proteins that we need to take into account. One is called myosin, that you already heard before, and one is called cadherin. Myosin is responsible for molecular motors, cadherin for the integrity of the junction between cells. Now, from two maps of this cadherin and myosin on top of this embryo, what we would like to predict that very complex motion of the cells on top of the embryo. We want to show how those cells are flowing. We want to output maps like this, only having this as an input. And this is a very tough task. And by combining our energies, we managed to do this for 15 minutes in the life of this embryo, when it goes from this shape to this already. So what you see here is a plot of the error that you see going down in time, and the square of the speed of which the cells move on top of the embryo, both in machine learning and in experiment. What I want to draw your attention to is that these two lines are on top of each other. And here there's a movie that is going to be playing again. Notice how these movies are very similar from each other. Indeed, these two lines, the red and the black, are on top of each other. Make it even more visual. Here are trajectories of representative cells on top of that embryos in the experiment and calculated from the machine learning. You can see they're very similar. You probably will see even better if we put it on top of each other. Okay, it's in fact quite astonishing. I'm going to show it again here. See the trajectory, experiment and machine learning. They don't differ very much. This is for 15 minutes the life. And what I would like to stress is that all of this was achieved by giving to a neural network only one snapshot, two proteins distribution at the beginning. And then the neural network predicted the next 15 minutes with no information other than what we're given. Now, this was quite striking, but it doesn't exhaust the full power of the full extent of our needs. In particular, one of the things that we've been putting a lot of effort recently is to face some challenges that arise, in particular in multicellular dynamics. In multicellular dynamics, the signal is very stochastic. What does that mean is that on top of an average velocity, there's a lot of noise. And sometimes the noise is bigger than the signal. And we actually predict even those situations. The second thing that happens is that it's important that this tissue is composed of discrete objects. You can't just describe it as a field or a velocity that coarse-grains the information at the microscopic level, because, for example, some of the cells are splitting. So you go from having one cell to two cells. These are discrete events that cannot be captured by a density of cells. And finally, there are feedback mechanism or complex interaction between cells and their neighbors. So what we did is we constructed a more sophisticated approach that involves so-called graph neural networks. This is work pioneered by Ming Han, who is in the audience, John Devaney, again, Margaret Gardell. The idea is you take a tissue and you make a graph. This graph is constructed having the center, the nuclei of each cell be the node of that graph. And then the edges of that graph, the connection between nearby cells. And the idea here is to use this reduced picture of a multicellular of tissue as a graph in conjunction with neural network techniques to predict how multicellular things work, processes work. Here is an experiment I'm going to show you here, playing on the left, where our collaborator, John Devaney, in Margaret Gardell group, imaged the motion of all these cells. Each of these dots here is a cell, these arrows moving around at the velocity of the cells. This is the same thing calculated by our machine learning algorithm. But just looking at these pictures is not so easy to see what's going on. What we did here on the right for you is to measure the average speed in this movie and in this movie, average over the whole sample. In red, in blue, there is the experimental data. In red, there is the machine learning. You will see that they're in very good agreement. The thing that is most striking, if we plot the variance of the signal, the error, loosely speaking, first of all, it's huge, this shaded area. And the machine learning, which is the dashed error, sorry, the pink error, really matches the variance that is in the experiment. In other words, we not only predict the average signal, we predict also the noise in a situation in which the noise is huge compared to the signal. This is really something very complicated to achieve by other means. Finally, I would like to draw your attention to something that is perhaps, in my eyes at least, the cherry on the cake. See, up to this point, we were studying geometry and physics to predict geometrical and physical things, like how things move. Here, we asked the different question. If I give you a network, how all the cells are connected with each other, and information purely about the geometry of that network, can you figure out the internal state of a cell? See, in a cell cycle, there are 3 states usually the cells can be. This is the internal information to the cell. We asked our neural network to guess that simply from the neighbors' information on how these things move. We can do that with 90% accuracy. In other words, we can infer internal machinery of a cell purely from geometric information. Now, with that, let me conclude this journey, try to tell you, normally in the classic view of physics, we study with things called symmetries, conservation laws like conservation of energy. Traditionally, these ingredients are sufficiently strong, restrictive, that we can identify variables that are important to understand the natures. It can be displacement, velocity, things that you're familiar with. And we can also find the equations that are satisfied by these variables. This gave rise to the subject of fluid and solid mechanics that underlie a lot of engineering applications. But virtually all of the examples that are introduced to you today are media, either engineered or natural one, which this standard approach simply doesn't work, either because all the symmetries and conservation laws are broken, and what we have to do is we have to revisit them, revisit our mathematical tools, but also complement them with machine learning techniques that allow us to extract from this type of data the correct models that will allow us to generalize for the next centuries this very old and established subject. Thank you very much for your attention.
Yeah, time for questions. Please. I was wondering if you think, so will machine learning be a companion for all of us in physics going forward?
Well, it's always difficult to make predictions about the future, and those who do usually are proven wrong about the future. It's always more interesting than what we can predict. In my opinion, yes, but I like the word companion. In my opinion, the power of these techniques for science is when they're put together with domain-specific knowledge. Even here, you saw that we could do a lot when we combine knowledge of the physics that we know is true with machine learning techniques. Or in alternative, machine learning techniques is a way of understanding in a physics agnostic way what is important so that we can direct our model building approaches. And while the examples drawn here are from biological world or the engineering world, these techniques are being applied from astrophysics to particle physics, I would say with equal success. The real question is always to interpret the outcome of this black box. This is something that we are trying to do by extracting equations from these neural networks that appear from the outside, extremely complicated things of which we understand very little.
On the, I'm an entomologist. On the Drosophila fruit fly egg, is that visualization? The method is a movie of the X-ray micro CT? Is that?
Yeah, well, so we have, this is microscopy, the one of the images. And then we have, I think this is fluorescent microscopy for the proteins. And the other one is excuse me, I'm trying to, standard microscopy, the one up here. Yeah. Standard is not the right word because the magician who can perform imaging at the accuracy is in the back of this room. And it's something I wanted to say. Some of these things are only possible because of advances in imaging, which bring essentially a ton of data that allows us to train these neural networks. High quality data, very high quality data.
I'm just going to ask about that central problem. I mean, you certainly try to fit or kind of work into equations of this machine learning, algorithm. But are you looking into any other ways to make this neural network less of a black box? Anything else other than what you showed today?
Yeah. Well, one thing that we can also do is that instead of making an educated guess of what the answer could be, we could write down all the terms that are allowed by symmetries in this problem, and then distill which ones the neural network is actually picking on. And this technique is also very effective. We've used it, and that is particularly good when you have absolutely no clue. But when you have a little bit of clue, it's good to put it in.
To what extent is interaction with nearest neighbor versus two-way, three-way?
Absolutely crucial. Yeah. Thank you very much for the question. This is something that, in the interest of time, I skimmed a little bit. This technique, these ideas about the graph. Give me 1 second. Graph neural networks that I was drawing is that often interaction between the cells are not pairwise. The way the cell interacts with that does not only depend on them. It depends also on cells quite far away from it. Okay. And another peculiarity is that the interactions are often directional, right? So I did that very fast, but see, 1, 2, 3, sequential. So what we had to really do is to tweak our neural networks to create two graphs. One graph, which is the one showed here, and a dual one that contains information about the interactions, so that we could allow for directional, path-dependent, and non-pairwise interactions that are absolutely crucial and dominant in this system. That actually is the most important technical things that Ying Han figured out to get this to work with this level of accuracy. And it was a challenge.
Can you give us some idea of how many people worked on this issue for how long to get the results that you're talking about today?
Yes, I can give you an idea. And there's a sinister word in this slide, which is in preparation. And that sinister word appears in everything I've shown you. And of course, there could be an element of perfectionism on the part of the authors of this thing, including myself. But all of these projects you've shown took at least 2 years and they're not completed. In part is also because we were constantly blown away by what we could do. And we go greedier and greedier. But that also entails the fact that there is a very enjoyable, maybe that's why we don't want it to end, interaction back and forward with experimentalists. The moment we can do something, we have more ideas of what we should be doing, and we're always happy to comply. But it's also tons of work, both at the level of coding, at the level of the intuition that goes in the models, the know-how from the experimentalist, both in terms of techniques to acquire the data, as well as suggesting us the important questions for the biology. It's really thrilling, but a sinister word that will probably be there a bit, hopefully not too long. Yes.
Is the fruit fly video available online?
I think so. Actually, there's a name that I would like to, Sebastian Streichen, who is in the audience, is at the University of California, Santa Barbara. And his webpage, it's, in my opinion, some sort of modern art exhibition in which the fruit fly embryo is staging constantly. And a good chunk of these movies are there. In particular, I think that this one has become one of the iconic movies of the field. They're literally the best data in the world on this system right now.
Okay. Any last questions?
Yeah.
Beautiful work on the flocking and stalling.
Yes.
It's not so much the geometrical distance that governs interaction, but the kind of topological distance.
How many names?
Do you see something similar with the cells?
Well, what goes on in the models in our model here is something way more complicated than that distinction. What I would say that those two categories are still caricature of the actual behavior that even cells display, leave it alone birds. So I would say that what we're seeing here, these directional interactions, non-mutual interactions, things that have not even been considered in full in models of flocking. One of the things that for me is the question that will keep me busy, but I have the arrogance to believe there's an interesting question for everybody. And it's certainly a question to which our chair, Greg, made an important contribution, is to try to put non-realistic models of animal behavior, of adaptive behavior of the individual components, and combine them with a collective description of a collection of such animals. Usually speaking, these models that you mentioned of flocks, treat the flocks as if they were arrows flying in the air, spins. I don't know how the birds feel about this characterization. I suspect that it's a bit playing down their intelligence. In reality, these animals are performing games. They have strategy they're optimizing. And one of the goals that I have is to use machine learning techniques with data from people who collect actual pictures of birds and try to develop theories of this type of fluids that know about those strategies that the birds are actually using it. And this is the first example of doing it, not with birds, but with cells. The answers are nowhere the type of simplified models that we would write down coming from physics.
Wonderful. Let's thank Vincenzo again.
Thank you.